My sincere greeting to one and all. My sincere greeting to one and all. I am Tamanna from BSc Chemistry Honor Second Year. Today I am here with chapter Aldehyde and Ketones. Introduction. Aldehydes and ketones constitute two isomeric series of compounds, both of which contain the carbonyl group C double bond O in their molecules and are therefore collectively known as carbonyl compounds. Aldehydes have one hydrogen atom and one alkyl or aryl group linked to the carbonyl group, while ketones have two alkyl or aryl groups attached to the carbonyl group. As shown below, aldehyde ketone R and R dash may be simple or substituted alkene or aryl groups. The aldehyde are said to contain the functional groups or simply CHO, commonly referred to as aldehyde group, while ketones contain the functional group C double bond O, generally termed as ketonic groups, which when present in ketones. Ketones in which the group R and R dash attached to the ketonic group are the same are termed as simple ketones, and those in which R and R dash represents different groups are known as mixed ketones. The presence of carbonyl group in both aldehyde and ketone is responsible for the close similarity in their method of preparation and properties. However, due to the presence of free hydrogen molecule in the molecule of aldehyde are more reactive than ketones and also differ from them in certain aspects. Structure of carbonyl group. The carbon-oxygen double bond of carbonyl group is composed of an pi bond and of a sigma bond and a pi bond. Moreover, in the molecules of aldehyde and ketones, the carbon atom of the carbyl group is also combined to two more atoms by a sigma bond. Thus, the carbonyl compound is involved in the formation of three sigma bonds and one pi bond. According to molecular orbital theory, the carbonyl compound of aldehyde and ketone make use of three sp2 hybridized orbitals in forming the three sigma bonds. As such, these bonds lie in the same plane with angle of approximately 120 degree between them. The pi bond between the carbon and oxygen is formed by the sideways overlapping of remaining half-filled p orbitals of carbon with a similar orbital of oxygen. The above discussion makes it clear that carbonyl group oxygen, carbonyl carbon, oxygen, and the two atoms directly attached to the carbon lie in one plane. The planar nature of the part of molecule which immediately surrounds the carbon is spotted by electron diffraction or spectroscopic studies of aldehyde and ketone. Another important aspect of the structure of carbonyl group arises from the different electronegativities of carbon and oxygen atoms. Due to its greater electronegativity and the oxygen atom attract the electrons of the double bond, partially the pi electron could strongly towards itself. As a result, the electrons are not equally shared and there is a greater density around the oxygen around the carbon atom. In other words, carbonyl group is polar group, oxygen having a small negative charge and carbonyl having the small positive charge. The polar nature of carbonyl group is probably best indicated by representing it as a resonance hybrid of the following two structures. The large dipole moment 2.3 to 2.8 diameter of aldehyde and ketone supports the polar character of the carbonyl group. Comparison of carbonyl group or ethylenic double bond. It may be interesting to note that the carbonyl group is similar to ethylenic double bond in many respects. Both of them first consist of a sigma bond and a pi bond. Both of them make use of sp2 hydrocarbon atom for the formation. Third, are planar in nature, and fourth, readily undergo addition reactions. However, the carbonyl group differs from the ethylenic bond in the following respects. First, carbonyl group is polar in character while ethylenic double bond is not. Second, it is not necessary that a reagent which added to the carbonyl group must also add to ethylenic double bond or vice versa. Third, addition reaction occurs. Carbonyl group are initiated by nucleophilic reagent while ethylenic double bond undergo electrophilic addition reactions. Nomenclature: Aldehydes. They are named either according to the common or IUPAC system as explained below. First, common system. In this system, aldehydes are named after the acid which they gives rise to on oxidation. The suffix "ic" added of the name of the acid is replaced by the word aldehyde. Thus, CH3CHO gives acetic acid on oxidation and it is therefore named as acetaldehyde. Similarly, benzene CHO forms benzoic acid on oxidation and is therefore named as benzaldehyde. This system is mainly used for aromatic and simple aliphatic aldehydes. Second, IUPAC names. These names are given in accordance with the journal IUPAC results. The longest chain carrying the CHO group is selected. The corresponding word root and the primary suffix "-ane", "-ine", "-ine" as required are written. This is followed by attaching the suffix "-al" in place of final "e". The position of substituents, if any, or indicated by stable numbers. The aldehydic carbon always gets the number first because of its chain terminating from group. For this reason, the number of aldehydic carbon is not usually mentioned. It is taken for granted that it must be numbered 1. For example, the compound CH3CH, CH3CH2CO is named as 3-methyl-butanol, and similarly CH3CH2C, CH3 double bond CH2CHO is named as 4-methyl-hexa-3-enol. For aldehydes in which the CHO group is attached to a ring, the suffix carbaldehyde is added to the name of the ring. For example, cyclohexane carbaldehyde, benzene carbaldehyde. Common and IUPAC names of some aldehydes. First is HCHO, formaldehyde, methanol, acetaldehyde, ethanol, propanaldehyde, propanol, isobutylaldehyde, 2-methyl-propanol, cetaldehyde, but-2-enol, benzaldehyde, benzene carbaldehyde, para-tolualdehyde or 4-methyl-para-methylbenzaldehyde is 4-methylbenzene carbaldehyde, phenylacetaldehyde, phenylethanol. Ketones. The two systems of naming ketones are as follows. First is common name. Common name of ketones are obtained by adding the word ketone to the name of alkyl or aryl group present in the molecule. These names are mainly used for aromatic or simple aliphatic ketones. For example, CH3COCH2CH3 is named as methyl ethyl ketone. Second is IUPAC names. IUPAC names of ketones carry the suffix "-one" and are given according to the usual rules. The longest chain containing the carbonyl group is selected. From the name of corresponding hydrocarbon, the suffix "-e" is replaced by "-one". The carbon of the ketonic group is assigned to the minimum possible number along the straight chain of carbon atom, and the substituent group carry other stable numbers. For example, CH3COCH2CH, CH3CH3 is named as 4-methyl-pentane-2-one. Certain ketones, particularly aromatic ketones, are allowed to retain their common names. For example, acetophenone, benzophenone. Some IUPAC and common names of some ketones. First, dimethyl ketone or acetone, propanone, methyl ethyl ketone, butanone, methyl and propyl ketone, pentane-2-one, methyl isopropyl ketone, 3-methyl 2-on cyclohexone, methyl phenyl ketone or acetophenone, diphenyl ketone or benzophenone, benzyl ethyl ketone, 1-phenyl butane 2-on, benzyl acetone, 2,4-phenyl but 3-ene 2-on. Formation of aldehydes and ketones. Formation of aldehydes. Aldehydes are formed during many chemical reactions. Of these, we would describe only the important reactions which are actually used for preparative purpose. For first, oxidation of primary alcohols. Aldehyde can be obtained by the oxidation of primary alcohols. However, this method suffers from a serious limitations because of aldehydes formed are further oxidized to carboxylic acid. This is primary alcohol on oxidation give aldehyde and further oxidation gives carboxylic acid. The oxidation of aldehyde to carboxylic acid generally takes place even the milder oxidizing agents than those required for the oxidation of primary alcohol to aldehyde. Therefore, it is difficult to stop the oxidation up to aldehyde stage. This problem can overcome if the aldehyde formed is removed from the reaction mixture by its distillation as soon as it's formed. This is often possible to do so because the aldehydes have lower boiling point than corresponding alcohols and they can be distilled away from the reaction mixture. For example, one propanol at whose boiling point is 370 Kelvin reacting with K2Cr2O7 and H2SO4 give propanol whose boiling point is 322 Kelvin. Another example is 1-butanol whose boiling point is 391 Kelvin on oxidizing with reagent K2Cr2O7 and H2SO4 gives butanol whose boiling point is 349 Kelvin. As shown above, the oxidizing agent usually employed in the above reaction is a solution of potassium dichromate in dilute sulfuric acid. However, if the alcohols have poor solubility in water, a solution of chromic anhydride CrO3 in water, acetone and sulfuric acid is commonly used. This is known as Jones reagent. Special oxidizing reagent. The above method of preparing aldehyde involving the distillation of aldehyde from the reaction mixture as soon as it formed cannot be used in case of higher aldehyde having high boiling point 373 Kelvin and above. Therefore, some special oxidizing agents have been developed for preparing aldehyde or ketone. These are first, Surtees reagent or Collins reagent. It consists of complex formed by careful addition of CrO3 to excess of pyridine C5H5N. CrO3 plus 2 moles of pyridine gives CrO3 C2H5N. Chromium trioxide pyridine complex. A solution of the above complex in methyl dichloride CH2Cl2 oxidizes to primary alcohol to the aldehyde stage. This is RCH2OH in presence of CrO3 2 moles of C5H5N. CH2Cl2 gives RCHO. First, Corey's reagent. It consists of pyridinium chlorochromate PCC, C5H5N H positive, CrO3Cl negative formed by mixing chromium trioxide, pyridine and HCl. It is used in methyl dichloro solvent to convert primary alcohol into aldehyde. Third, pyridinium dichromate PDC, C5H5N H positive twice, Cr2O7 2 negative. It is obtained by mixing pyridine and potassium dichromate and HCl in CH2Cl3. 2 moles of C5H5N plus 2 moles of HCl plus K2Cr2O7 on oxidation in presence of CH2Cl gives C5H5NH positive twice, Cr2O7 2 negative plus 2 moles of KCl. Advantages of oxidation of alcohols with above reagent. As it obvious advantage of using any of the above three reagent is that they restrict the oxidation of primary alcohol to aldehyde stage. This is because these reagents are used in non-aqueous medium and therefore do not allow the formation of aldehyde hydrates RCHOH twice to take place during oxidation. Since aldehydes themselves are not easily oxidized further as aldehyde hydrates, the reaction stop at aldehyde stage. In case of oxidation by usual oxidizing agents such as acidic potassium dichromate and Jones reagent, the reaction are carried out in aqueous medium where aldehyde formed are converted into aldehyde hydrides, which are readily oxidized to carboxylic acid. Another advantage of using these reagent is that carbon-carbon double bond, if present in the starting alcohol, are not oxidized. For example, 5-methylhexane for 4 in 1 ol in presence of PCC gives 5-methylhex 4 in Al. Enol. Disadvantages of using above reagents: the use of special reagent discussed above for the oxidation of alcohols lead to the formation of chromium containing waste products which are environmentally very hazardous. At the same time, these reagents are quite expensive and are therefore not frequently used during laboratory oxidation reaction of alcohol. Second disadvantage: catalytic dehydrogenation of primary alcohols. The oxidation of primary alcohols to yield aldehyde can also be brought about by passing the alcohol vapors over copper heated to 475 to 575 Kelvin. This process is generally referred to as dehydrogenation as it involves the direct elimination of hydrogen. Primary alcohols in presence of copper at the temperature 475 Kelvin to 575 Kelvin give aldehyde plus H2, and propyl alcohols in presence of Cu 475 to 575 Kelvin gives propanonaldehyde. The dehydrogenation process does not involve the risk of further oxidation of aldehyde formed. Another efforts Second, catalytic dehydrogenation of primary alcohols. The oxidation of primary alcohols to yield aldehyde can also be brought about by passing the alcohol vapors over copper heated at 475 to 575 Kelvin. This process is generally referred to dehydrogenation as it involves the direct elimination of hydrogen. The dehydrogenation process does not involve the risk of further oxidation of aldehyde formed. Third, reduction of aldehyde chlorides. Rosenberg reaction. The partial reduction of acid chloride affords another method for the formation of aldehydes. The reaction is usually brought out by passing hydrogen through a hot solution of acid chloride in xylene in the presence of a suitable catalyst. The catalyst employed is palladium, partially poisoned by sulfur or quinine deposited on barium sulfate, and the reaction is stopped as soon as the evaluation of HCl gas ceased. This helps to prevent further reduction of aldehyde formed into alcohol. Acid chloride in presence of PdBSO4 gives aldehyde plus HCl. Nowadays, lithium tetrabutoxyaluminum hydride LiAlH4OC CH3 into thrice is being used to reduce acid chloride into aldehyde. An advantage of using this reagent is that if it does not affect any other easily reducible group present in the molecule. Para-nitrobenzoyl chloride gives para-nitrobenzaldehyde in the presence of LiAlH OCCH3 thrice over twice in 195 Kelvin temperature. Acid chlorides used in the reaction are themselves usually obtained by the action of thionyl chloride or phosphorus aldehyde on carboxylic acids. This is RC double bond OHO plus SOCl2 gives RC double bond OCl plus SO2 plus HCl. This aldehyde can be obtained from carboxylic acid through the formation of acid chlorides. Fourth, from 1,3-dithenes. The most recent method of synthesis of aldehyde is by the use of 1,3-dithesis. 1,3-dithesis or 1,3-dicyclohexane is a non-aromatic heterocyclic compound containing two sulfur atoms. It can be easily converted into its anion by treating with alkyl lithium. The anion acts as a strong nucleophile and react with alkyl halide SN2 reaction to form alkyl derivative of 1,3-diethene. This derivative is hydrolyzed in the presence of Hg2 positive ions to form the aldehyde. The complete sequence of the reaction is given below. 1,3-diethanes itself may be prepared by the reaction of propane 1,3-diethiol with formaldehyde in a weakly acidic medium as follows. Fifth, catalytic decomposition of carboxylic acid. Aldehyde can be obtained from carboxylic acid by passing the vapors of the mixture of methanoic acid and another carboxylic acid over magnesium oxide at 573 Kelvin temperature. Some other methods which can also be used for the preparation of aldehyde are given below. 6. Ozonolysis of alkenes. In this method, the ozonide formed by the reaction between the alkenes and ozone is decomposed with a reducing agent Zn plus acetic acid or hydrogen or palladium to yield aldehyde and ketone. 7th, Stephen reaction. Alkyl cyanide on reduction with stannous chloride and hydrochloric acid give rise to aldehyde. The aldehyde gets hydrolyzed on warming with water to yield an aldehyde. 8th, oxidation of methyl benzenes. Aromatic aldehydes can be prepared by the oxidation of methyl benzenes by different methods as given below. First, oxidation of methyl benzene to aldehyde is usually carried out with chromium trioxide in acetic anhydride. The diacetic in which the two acetic groups are attached to the same carbon atom initially formed is isolated and hydrolyzed to get the aldehyde. Since the intermediate gem diacetate cannot be oxidized further, there is no chance of the formation of carboxylic acid. Second, controlled oxidation of methyl benzene to aldehyde can also be carried out with chromyl chloride or manganese dioxide. The reaction involving chromyl chloride as oxidizing agent is known as Itard reaction. For example, toluene in presence of 2 moles of CrO2Cl gives addition complex, then on hydrolysis H2O gives benzaldehyde. Third, it is also possible to convert methyl benzene into aldehyde by free radical halogenation of methyl benzene followed by hydrolysis of gem dihalides formed. For example, toluene is heated plus 2 moles of Cl give benzyl chloride. 9th, Gattermann-Koch reaction. The reaction consists a convenient method for preparing aromatic aldehyde by treating benzene or other aromatic compounds with a mixture of CO and HCl in the presence of a Lewis acid and copper 1 chloride. In a similar reaction as Gattermann's reaction, HCl is used in the place of CO. The aluminide initially formed is hydrolyzed to get the corresponding aromatic aldehyde. 10th, Rimmer-Tiemann reaction. This is an convenient method for the preparation of phenolic aldehyde
particularly those in which the aldehyde group is present in ortho position to the phenolic group. The reaction is carried out by treating the phenol with chloroform and aqueous sodium hydroxide solution. Formation of ketones. The important method of preparing ketones are described below. First, oxidation of secondary alcohols. Ketones can be easily prepared by the oxidation of secondary alcohols. The oxidation is usually effected by acidified sodium or potassium dichromate, potassium permanganate, or chromium trioxide in a variety of solvents. There is no risk of further oxidation of ketone taking place as ketones are not easily oxidized. Off-on-air alcohol oxidation. Secondary alcohols can also be oxidized by refluxing with acetone in the presence of aluminium isopropoxide CH3 2CH or thrice Al or aluminium tetrabutoxide CH3 thrice CO whole thrice Al. The alcohol taken is oxidized to the corresponding ketone while acetone is reduced isopropyl alcohol. The process is particularly stable for oxidation of unsaturated alcohol and is known as off-inner alcohol oxidation. Second, catalytic dehydrogenation of secondary alcohol. Ketone can also be obtained by the dehydrogenation of secondary alcohols by passing their vapors over copper heated at 475 to 575 Kelvin temperature. Secondary alcohols gives ketone in the presence of copper. Temperature is 475 to 575 Kelvin. Similarly, another example is isopropyl alcohols give acetones plus H2 in presence of Cu 475 Kelvin to 575 Kelvin temperature. Third, reaction of nitriles with Grignard reagent or organolithium compound. Reaction of an anhydride with either a Grignard reagent or any alkyl lithium followed by hydrolysis of a ketone. The reaction's mechanism is given below. Fourth, reaction of a acid chloride with organocadmium compound. Acid chloride react with suitable organocadmium compounds to yield ketones. Acid chloride plus dialkyl or diaryl cadmium gives 2 moles of RCOR- plus CdCl. R may be any alkyl or aryl group, but R- must be an aryl or primary alkyl group. This is because organocadmium compound containing only aryl or primary alkyl group are sufficiently stable for use. Benzoyl chloride, 2 moles of benzoyl chloride plus dimethyl cadmium gives acetophenone plus CdCl2. These days, another type of organometallic compound known as lithium organocuprates R2CuLi, where R may be an alkyl or aryl group, are being increasingly used for preparation of ketones from acid chlorides because the reactions involved does not suffer from any drawbacks. 2 moles of RC double bond OCl plus R-2CuLi gives 2 moles of RCOR- plus CuCl plus LiCl. R and R- may be any alkyl or allyl group. Lithium organocuprates are themselves obtained by reaction between cuprous halides and organolithium. 2 moles of RLi plus CuX gives R2CuLi plus LiX. Since acid chlorides can themselves be obtained from carboxylic acid, the above reaction enable us to prepare ketones from carboxylic acid. Fifth, reaction of carboxylic acid with alkyl or aryl lithium. When a carboxylic acid is treated with 2 molar equivalent of alkyl or allyl lithium, followed by a reaction of water, it leads to the formation of ketone. The mechanism is given below. Carboxylic acid plus alkyl or allyl lithium gives the following product. The net reaction may be represented as For example, RC double bond OOH gives in presence of 2 moles of R dash Li and H2O. Further followed by H2O gives RC double bond O R dash plus RH 2 moles of LiOH. For example, hexanoic acid gives 2 heptanone plus methane plus 2 moles of LiOH. Ketones can also be obtained by distillation of calcium salts of carboxylic acid other than formic acid. For example, calcium acetate distilled give acetone. 6. From 1,3-dithesis, not included in syllabus but we shall study it. The reaction involves the conversion of 1,3-diethene into their dialkyl derivative in two stages. The subsequent hydrolysis of the dialkyl derivative to form ketone. Friedel-Crafts acylation. This method is specifically used for the preparation of ketones in which the ketonic group is attached to at least one aromatic ring. It consists in treating an aromatic compound with an acid halide in the presence of a Lewis acid such as anhydrous aluminium chloride. Aromatic compound plus acid chloride give ketone or may be any alkyl or allyl group. The reaction will take place in the presence of anhydrous AlCl3. It is also possible to use an acid anhydride in place of acid chloride. For instance, benzene plus acetic anhydride gives acetophenone plus benzoic acid plus ethanoic acid. Some other methods which can also be used for the preparation of ketones are given below. 8th, hydration of alkenes. Hydration of homologous of acetylene leads to the formation of methyl ketones. For example, 2-butene gives methyl ethyl ketone in presence of HgSO4 and H2SO4. 9th, ozonolysis of alkenes. Ozonolysis of alkenes in which the double bond is next to the position of branching of the carbon chain also leads to the formation of ketones. For example, 2,3-dimethyl 2-butene gives acetone in presence of H2O-Zn. 10th, acetoacetic ester synthesis. Methyl ketone can be conveniently obtained from alkyl derivative of ethyl acetate, popularly known as acetoacetic ester. The method involves the treatment with alkyl halide yields a conversion of acetoester into pseudoacetoacetic ester by treatment with sodium ethoxide. Subsequently, treatment with alkyl halide yields alkyl acetoacetate ester. This is subjected to hydrolysis and the beta ketone acid thus obtained is heated to get methyl ketone. For example, acetoacetic ester in presence of C2H5ONa gives soda acetoacetic ester. Then further reaction with RX minus NaX gives alkyl acetoacetic ester. Further with OH gives alkyl acetoacetic acid and then on heating give methyl ketone. Physical properties of aldehydes and ketones. First, physical state. With the exception of formaldehyde, which is a gas at room temperature, most of the common aldehyde and ketones are liquid at ordinary temperature. The lower molecular weight aldehyde have sharp and rather unpleasant smell, but high molecular weight aldehyde and ketone are pleasant smelling. In fact, some ketones are used in perfumes. Second, boiling point. The boiling point of aldehyde and ketones are lower than those of alcohols and carboxylic acid of approximately equal molecular weight. This is due to the fact that unlike alcohols and acids, they are not effective hydrogen bonds between aldehyde or ketone molecules. However, due to their highly polar nature, there is appreciable intermolecular attraction in aldehyde or ketones. As such, these boiling points are higher than those of hydrocarbons and esters of comparable molecular mass. Weight. Melting and boiling point of some aldehyde and ketones are shown in the table. Table 7.3 lists the melting and boiling point of some aldehydes and ketones. It is obvious that the boiling point rises with the increase in molecular weights. Third, melting point. Melting point of aldehyde and ketone do not show any regular trend with increase in molecular weight, as it is clear from table 7.3. Fourth, solubility. Aldehydes and ketones contain up to 5 carbon atoms, are more or less soluble in water, but the solubility falls rapidly with increasing molecular weight. Higher member as well as aromatic aldehyde and ketones are practically insoluble. However, all aldehyde and ketones are readily soluble in organic solvent. The solubility of lower aldehyde and ketone in water is due to the formation of intermolecular hydrogen bonds involving the carbonyl group as shown ahead. But the increase in the size of the non-polar group attached to the carbon atom does not allow hydrogen bonds to take place, so the solubility decreases sharply with the increase in molecular weight. Chemical properties of aldehyde and ketones. Aldehyde and ketones are highly reactive compounds which exhibit a marked similarity in their chemical behavior. This is of course due to the presence of carbonyl group in both type of compounds. But an important question which arises is as what makes the carbonyl group so reactive, and what type of reaction does it bring about in aldehyde and ketone. It would quite appropriate to deal with the question before discussing the actual chemical reaction. Reactivity of carbonyl group towards nucleophilic attack. The carbonyl group contains a double bond between two heteroatoms, carbon and oxygen, since is more electronegative than carbon. The bonded electron, particularly the pi electron, are pulled strongly towards oxygen. As a result, the carbonyl group is very popular group. The carbonyl carbon being electron deficient in acidic, the carbonyl oxygen being electron rich, example basic. Moreover, the carbonyl group is flat and can therefore be readily attacked from above or below in a direction perpendicular to the plane of group. Consequently, the carbonyl group is highly reactive group. It is quite obvious that the reaction of the polarized carbonyl group could be initiated either by the attack of nucleophile reagent, basic or electron deficient carbon, or attack of an electrophile reagent on the electron rich oxygen. However, out of the electron deficient carbon and electron rich oxygen, the former is relatively less stable. Therefore, most of the reaction of aldehyde and ketone involve the initial attack of nucleophile reagent on the relatively less stable electron deficient carbonyl carbon, and ultimately leads to the formation of addition product. As such, these reactions are described as nucleophilic addition reactions. Mechanism of nucleophilic addition reaction. The nucleophilic addition reaction to carbonyl compound is initiated by the attack of nucleophile on the carbonyl carbon. This leads to the formation of a transition state in which the hybridization of the carbon changes from sp2 to sp3. At the same time, oxygen being to acquire pi electrons of C double bond O bonds as shown below. Carbonyl compounds, transition state, tetrahedral intermediate, and addition product. As the pi electrons of C double bond O bonds are completely transferred to oxygen, a tetrahedral intermediate is formed in which carries negative charge. This intermediate picks up a proton, usually from H2O, used as solvent. To form the addition product, the attacking nucleophile reagent can be either a negatively charged ion, such as Cn negative and carbonium ion, or a neutral molecule. It may be noted that it is the ability of oxygen to acquire electrons or to accommodate negative charge which seems to be primary cause of reacting of carbonyl groups toward nucleophilic reagent by the attack of carbonyl carbon. Role of acid catalyst in nucleophilic reaction. The nucleophilic attack on the carbonyl group can be catalyzed by the presence of acid. The hydrogen ion generated by the acid rapidly combine with the electron-rich oxygen of the carbonyl group. This leads to the decrease in EAC activation energy for nucleophilic attack as it enables oxygen to acquire the pi electron without having to accommodate a negative charge as shown ahead. It should be noted, however, that if the reaction solution is made too acidic, the H positive ion would combine with the attacking nucleophile reagent as well. This would suppress the concentration of attacking nucleophile species and thus adversely affect the nucleophilic attack. Therefore, it is important to control the pH of reaction mixture in such reactions. It should be noted that addition of powerful nucleophiles does not require any acid catalyst at all. It is only the weak nucleophile such as alcohol and ammonia derivative which needs to assist of a little acid catalysis. Relative reactivity of aldehyde and ketone in nucleophilic reaction. It has been observed that in nucleophile addition reaction, aldehyde are more reactive than ketones and aliphatic aldehydes or ketones are more reactive than in aromatic ones. This can be easily explained in terms of steric or electronic factors as discussed below. First, steric factor. The transition state of nucleophile attacked on carbonyl carbon. The carbons start forming a bond with the attacking species and tends to change their trigonal or tetrahedral state. Now the larger the size of alkyl or aryl group attached to the carbon group, the more crowded will be the transition state. As the transition state gets more and more crowded, the steric hindrance of these groups increases and the formation of the transition state becomes more and more difficult. Thus, the formation of transition state would be more difficult in case of ketones and in case of aldehyde since ketone contain two allyl or aryl groups attached to the carbon at group, while aldehyde have one hydrogen and only one alkyl or aryl group. As such, ketones would be less reactive than aldehydes. Similarly, amongst the ketones themselves, those containing bigger groups would be less reactive than one containing smaller group. Second, electronic factors. The addition through the steric factor, electronic factors are also responsible for the greater reactivity of aldehydes as explained below. First, aliphatic aldehydes and ketones. Aryl groups have electron releasing inductive effect and their presence tends to destabilize the transition state by enhancing the negative charge developing on oxygen. Since aldehyde contain only one alkyl group while ketone have two such groups, the transition start resulting from a ketone is destabilized to greater extent than that resulting from an aldehyde. As a result, such the transition state is more difficult to form in case of ketones and consequently ketones are less reactive. It can also be understood that the presence of electron-attracting substituent on alkyl group would enhance the reactivity of aldehyde and ketones in nucleophilic reaction. Second, aromatic aldehydes and ketones. An aromatic nucleus directly attached to carbonyl group may be accepted to increase the reactivity of aldehyde and ketone as it tends to stabilize the transition state due to its electron withdrawing inductive effect. However, the electromagnetic nucleus stabilizes the reacting aldehyde or ketone even more due to the resonance interaction with the pi electrons as shown below. The result is that aryl group cause a net decrease in the reactivity of carbonyl group. As such, aldehyde or ketone having aryl group directly attached to the carbonyl group are less reactive than aliphatic counterpart. It may be noted that the presence of electron withdrawing substituent such as NO2 and CN at ortho and para position of the benzene ring increase the reactivity of aromatic aldehyde and ketone. Electron donating groups such as R, OH and OR have the opposite effect. Acidity of alpha hydrogens. Besides providing a site for nucleophilic addition reaction at aldehyde and ketones, the carbonyl group is also responsible for the acidity of alpha carbon atom. In the presence of a base, a hydrogen attached to the alpha carbon atom can split off into the form of H positive ion to form a carbanion. The carbon anion thus formed accounts for further many reactions for aldehyde and ketones. The acidic nature of alpha hydrogen and its removal in presence of a base can attribute to the fact that the resulting carbanion is resonance stabilized by interactions with the carbonyl group as shown below. It is interesting to note that the participation of carbyl group in the resonance stabilization of the carbon is due to the ability of oxygen to accommodate the negative charge. Ionization of beta and gamma hydrogens of saturated aldehyde or ketone. It is not possible as the resulting carbanion would not be resonance stable. Crystalline solids refers to as bisulfide addition compounds. In these compounds, carbonyl carbon get bonded to sulfur of the attacking reagent. It is a reversible reaction, but on using saturated solution of sodium bisulfate, the equilibrium is shifted to the right and the addition product get precipitated. Ketones containing bulky groups do not react with NaHSO3 due to steric hindrance mechanism. The reaction involves nucleophilic attack of the carbonyl carbon by bisulfite ions, and the complete process may be depicted as shown below. The bisulfite addition compound decomposes on forming with dilute acid or base to give back the original carbonyl compound. Therefore, the formation of bisulfite compound is used for the purification of carbonyl compounds, particularly aldehydes from non-carbonyl impurities. Second, reaction with ammonia derivatives. Aldehyde and ketone undergo nucleophilic addition with certain compounds related to ammonia such as hydroxylamine, hydrazine, phenylhydrazine, semicarbazide. The addition compound initially formed eliminate a molecule of water to yield compounds containing a double bond between carbon and nitrogen of the attacking reagent. As such, these reactions are also termed as addition-elimination or condensation reaction. If we represent the ammonia derivative by the general formula H2NG, where G may be OH, NH2, NHC6H5 or NHCO, NH2, etc., the formation of a final product may be depicted as aldehyde or ketone plus ammonia derivative give initial addition compound, then further with reaction in presence of minus H2O gives final product. The product formed are usually crystalline solids having sharp melting points and are used for the identification of aldehydes and ketones. Moreover, as these products can also be decomposed by boiling with dilute mineral acid to regenerate the parent carbonyl compound, they can also be used for the purification of aldehydes and ketones. Mechanism. All the amino derivatives represented by formula H2NG are basic compounds having a lower pair of electrons on nitrogen. They act as weak nucleophilic reagent and their reaction with carbonyl compound is catalyzed in presence of acid. The hydrogen ions protonated the carbonyl oxygen, and as a result the carbonyl carbon is very rapidly attacked by basic nitrogen compound. The additive thus formed subsequently changes to the final product as shown below. Reaction conditions. Control of pH. It must be pointed out that while using acid as a catalyst in these reactions, it is very important to have proper acidity in reaction mixture. If reaction mixture is made highly acidic, the hydrogen ion must begin to protonate the attacking ammonia derivatives too. The protonated derivatives H3 and positive G does not have any unshared electron on nitrogen and so no longer nucleophilic. This naturally means that too much acidity would decrease the rate of reaction rather than catalyze it. In other words, the reaction medium should be have just right acidity or pH about 5 to ensure maximum rate of reaction. Ammonia derivatives used as nucleophile reagent in these reactions are usually employed in the form of their salts such as hydroxyl chloride and hydrogen sulfide in the presence of sodium acetate. From these salts, the attacking nucleophile reagent is produced in situ such as below. Hydroxylamine hydrochloride further reaction with produce give NH2OH NaCl plus acetic acid. The important reaction of ammonium derivative are discussed below. First, reaction with hydroxylamine. Aldehyde and ketone react with hydroxylamine to form oximines. Second, reaction with hydrazine. Aldehyde and ketone react with hydrazine to form hydrazones. Third, reaction with phenylhydrazine. Reaction of aldehyde and ketone with phenylhydrazine result in the formation of phenylhydrazone. In place of phenylhydrazine substituent, phenylhydrazines are also frequently employed. The most commonly used substituent phenylhydrazine is 2,4-dinitrophenylhydrazine Brady reagent, which rapidly react with aldehyde and ketone to form yellow, orange or red precipitate of 2,4-dinitrophenylhydrazones, commonly known as 2,4-DNP. Fourth, reaction with semicarbazide. Both aldehyde and ketone react with semicarbazide, forming semicarbazones. Reaction with ammonia. The reaction of aldehyde and ketones with ammonia are of no importance. Most of the aldehydes initially form addition product with ammonia known as aldehyde ammonia. These compounds are unstable and water to form a diene in which trans get polymerized. For example, acetaldehyde gives acetaldehyde ammonia which is unstable, then further give aldehyde and then on polymerization gives CH3CHNH thrice. Formaldehyde react differently to form hydromethyl hexamethylene tetraamine which is used as urinary antiseptic under the name urotropine. Formaldehyde plus 4NH3 gives hexamethyltrimine. Structure of hexamethyltetramine. Benzaldehyde react with ammonia to form hydrobenzamide. Ketones generally give complex polymers product with ammonia. The reaction of aldehyde and ketone with primary and secondary amine to form amines or enantiomers is discussed later in next chapter, chapter 10. Third, addition of alcohols. Alcohols and ketones react with alcohols in presence of anhydrous acid catalyst such as HCl gas to form aldehyde compound called acetals. Acetal contain new bonds between carbonyl carbon and oxygen atom of the alcohol. The product formed by the reaction between ketones and aldehydes were earlier called ketols, But now the term acetal is used for the product formed from aldehyde as well as ketones. Mechanism: to start with a molecule of alcohol added to the carbonyl group of the aldehyde to form a hemiacetal. With a few exceptions, the intermediate hemiacetal is not stable enough to isolate. On the other hand, under the catalytic influence of acid, the hemiacetal is readily converted into a stable acetal. It may be noted that the conversion of hemiacetal into acetal involves the replacement of OH by an alkoxy group, and its mechanism is similar to SN1 mechanism for the formation of an ether from any alcohol. Formation of cyclic acetal: both aldehyde and ketone react with ethylene glycol in the presence of para-toluene sulfonic acid (PTS) to yield respectively cyclic acetals. For example, cyclic acetal uses of acetals as protecting groups. Unlike aldehydes and ketones, acetals are very stable to bases, but are hydrolyzed back to aldehyde and ketone upon treatment with acids. Therefore, their formation is used as a mean of protecting a carbonyl group in certain reactions where it may otherwise interfere with a desired reaction. Protection is the process of preventing a group from taking part in any undesired reaction by converting it into a new, less reactive group from which it can be regenerated at a later stage. For instance, let us imagine that we want to carry out the reduction of ester group of a ketoester into an alcoholic group. The reducing agent which brings about the reduction of ether group would normally reduce the keto group as well. Therefore, selective reduction of ether group is not possible. The problem can be solved by first converting the keto group into an acetal. The resulting acetal in them subjected to reduction with LiAlH4, when ester group would be reduced to alcohol, but acetal would remain unaffected. The acetal group is then hydrolyzed back or keto group with aqueous acid. This illustrated below by considering the formation of 4-hydroxypentane 2-on from ethyl 4-oxopentanoate. Ethyl 4-oxopentanoate in presence of HOCH2 in CH2OH H positive gives cyclic acetal keto group protected. Further, in presence of LiAlH4 ester plus 3 H3OH O positive give ester group reduced to alcohol. Further, with H3O positive gives 4-hydroxypentane 2-on keto group regenerated. Nucleophilic addition reaction leading to the formation of carbon-carbon bonds. Carbonium as nucleophilic reagent. We would now take up reaction in which carbonium constituent the attacking nucleophile reagent. Most of these reactions are of great synthesis importance since they lead to the formation of carbon-carbon bond. Of these reaction of fourth, addition of hydrogen cyanide. Hydrogen cyanide add at most all aldehyde and ketones to form alpha hydroxynitrile, usually known as cyanohydrines. Hydrogen cyanide is produced in situ by dissolving NaCN or KCN in water and then slowly adding a mineral acid to adjust the pH of solution at 10. Mechanism: the reaction involves the initial nucleophilic attack of carbonyl carbon by a strongly basic carbonium, for example cyanide ions. The process is completed by the attachment of an hydrogen ion to oxygen. Cyanohydrazine are useful synthetic substances because they can be easily converted into compounds having new functional groups as illustrated below. First, the alcoholic part of cyanohydrin can undergo acid catalyzed dehydration to form unsaturated nitriles. For example, acetaldehyde gives acrylonitrile. They are readily hydrolyzed to form carboxylic acid. Third, the nitrile group present in them can be reduced into a primary amine by catalytic hydrogenation. For example, benzaldehyde cyanohydrin in presence of nickel give 2-amino 1-phenylethanol. Fifth, addition of Grignard reagent. Grignard reagent and other organometallic compound react with aldehyde or ketone to form an addition product which are readily decomposed by water, preferably in presence of an acid such as HCl or H2SO4 to yield alcohol. Acid aldehyde plus or ketones plus RMGX gives addition product. Then with further plus H3O positive gives alcohol plus MgXOH. Mechanism: the formation of addition product, the nucleophilic carbonium portion, for example, the organic part of the Grignard reagents, adds to the carbonyl carbon will be the remaining portion get attached to the oxygen as depicted below. This is followed by hydrolysis of addition product. It may be pointed out that depending upon the starting aldehyde or ketone, the alcohols obtained as the final product may be primary, secondary, and tertiary alcohols. Formaldehyde yields a primary alcohol, other aldehydes give secondary alcohols, while ketone furnishes tertiary alcohols. Sixth, addition of salts of terminal alkynes. When treated with terminal alkynes in the presence of sodium and lithium ammonia, addition of sodium salt of alkyl to the carbonyl group take place. The product formed on acidification give rise to alcohols which also contain carbon-carbon triple bond. The alkynols formed above can be converted into other compounds by reaction involving the OH group or carbon-carbon triple bond. Mechanism: the reaction involves the nucleophilic attack of carbanion of the terminal alkynes on the carbonyl group as shown below. Reformatsky reaction. This reaction consists in treating an aldehyde or a ketone with an alpha bromoester and metallic zinc in the presence of dry ether or benzene. The aldehyde product initially alpha bromoester and metallic zinc in the presence of dry ether or benzene. The addition product initially formed is decomposed in the presence of dilute mineral acid to yield beta hydroxy esters. Mechanism: the mechanism of Reformatsky reaction is similar to the Grignard reagent. Zinc is used in place of magnesium because organozinc compound, being less reactive than Grignard reagent, react only with carbonyl group of aldehydes or ketones and not with ester groups. The complete mechanism of the reaction may be depicted as follows. Beta-hydroxy esters undergo acid-catalyzed dehydration to form alpha-beta unsaturated esters. For example, ethyl-3-hydroxybutanoate gives ethylbutane 2-enate. Aldol condensation. In the presence of dilute base, 2 moles of an aldehyde or ketone having alpha hydrogen atom combines to form a beta hydroxyaldehyde or beta hydroxyketone. The hydroxyaldehyde obtained forms aldehydes which originally named aldol, aldehyde alcohols, and consequently the reaction come to be known as aldol condensation. For example, acetaldehyde plus acetaldehyde gives 3-hydroxyl-butanol aldol. It may be noted that every case the product contains the carbon-carbon bond between the carbonyl carbon of the one molecule and the alpha carbon of the second. mechanism. The base removes an alpha hydrogen from aldehyde or ketone molecules to form a resonance stabilized carbonium or enolate ion. This ion, being strongly nucleophilic, attack the carbonyl carbon for a second molecule of aldehyde or ketone to yield an anionic intermediate. The intermediate then abstract a proton from water to form the aldol. The complete mechanism is illustrated below by considering the example of acetaldehyde. This is important to note that aldol condensation can occur only due to the acidic nature of alpha hydrogens of carbonyl compound. Therefore, aldehydes or ketones such as formaldehyde, benzaldehyde, and benzophenone, which do not contain any alpha hydrogen atom, do not undergo simple aldol condensation. This is because such aldehydes or ketones can not form resonance stabilized carbonium ion. Synthetic importance. The beta hydroxyaldehyde or beta hydroxyketones obtained from base catalyst aldol condensation are easily dehydrated on warming with acid to form alpha beta unsaturated carbonyl compounds. For example, aldol form H positive H2O gives crotonaldehyde. Alpha beta unsaturated carbonyl compound in turn can be oxidized to alpha beta unsaturated acid or reduced selectively to the alpha beta unsaturated alcohol. Therefore, aldol condensation commands considerably synthetic importance. It can be employed for the preparation of beta hydroxycarbonyl compound, alpha beta unsaturated carbonyl compound, alpha beta unsaturated carboxylic acids, alpha beta unsaturated alcohols, etc. Cross aldol condensation. Aldol condensation can also take place in molecules of two different aldehydes or ketones or an aldehyde or a ketone. Such an aldol condensation is referred to as crossed aldol condensation if both the reacting carbonyl compound contain alpha hydrogen atom. Crossed the aldol condensation can yield a mixture of four different products which are usually quite difficult to separate. Therefore, such a reaction is seldom carried out. However, if one of the reactant does not contain any alpha hydrogen, the reaction can yield a mixture of only two products. Moreover, by a suitable choice of experimental conditions, it is possible to suppress the formation of one of the products so as to get only one compound as a main product. For example, if acetaldehyde, which contains alpha hydrogen, is slowly added to a mixture of benzaldehyde, which does not contain any alpha hydrogen, and aqueous alkene, the final product is mainly cinnamonaldehyde, obtained by the dehydration of initial formed beta hydroxyaldehyde. Benzaldehyde plus acetaldehyde in presence of OH negative gives benzene CHO gives cinnamonaldehyde. Similarly, reaction between acetone, which contain alpha hydrogens, and formaldehyde, which does not have any alpha hydrogen, yield mainly 4-hydroxy 2-butanone. Formaldehyde plus acetone minus OH give 4-hydroxy 2-butanone. It may be pointed out that in cross-aldol condensation, the aldehyde or ketone lacking in the hydrogens cannot form the attacking carbanion. It merely serves as a site for the nucleophilic attack by carbonium formed by the other reactant. Aldol condensation can also take place in the presence of acids. However, the acid catalyst condensation is not so effective, and addition product initially formed readily undergo dehydration to alpha beta unsaturated carbonyl compound as the final product. Mechanism. Acid catalyst aldol condensation take place by the following mechanism. In the presence of acid, the carbonyl compound is partially converted into enoic form such as shown below. Acetone gives ethanol. The enol act as a nucleophilic and attack a second molecule of protonated carbonyl compound form an intermediate. This loses the proton to form the condensation product, second molecule of protonated carbonyl compound. The condensation product thus formed readily undergo acid catalyzed dehydration to the alpha beta unsaturated carbonyl compound as the final product. Ninth, Claisen-Smith reaction or Claisen reaction. The reaction is a special case of cross-aldol condensation and may be defined as the base catalyst condensation of an aromatic aldehyde and an aliphatic aldehyde or ketone to form alpha-beta unsaturated aldehyde or ketone. For example, the reaction between acetaldehyde and benzaldehyde in presence of aqueous alkali yields mainly cinnamaldehyde. In the above reaction, initially two products are obtained. One is the self-condensation product of acetaldehyde, while the other is the crossed condensation product, which is the main product. This product, in which beta OH group is activated by phenyl group, loses water immediately to form alpha beta unsaturated aldehyde. Similarly, reactions between benzaldehyde and acetone in the presence of aqueous alkali yields benzyl acetone. Mechanism. The mechanism of the reaction is similar to base catalyst aldol condensation. Benzone condensation. Aromatic aldehyde which do not contain alpha hydrogen atom cannot undergo simple aldol condensation. However, in the presence of potassium cyanide, they undergo self-condensation in a different manner to form product known as benzonium. For example, benzaldehyde gives in presence of KCN benzoin. Mechanism. The reaction is generally believed to proceed as follows. Third, 11th, Perkin reaction. Closely related to aldol condensation is the Perkin reaction, which involves the addition of acid anhydride to aromatic aldehyde in the presence of bases. The base commonly employed is the sodium salt of carboxylic acid form, which the anhydride is derived and the addition compound initially formed ultimately ald and alpha beta unsaturated acid. For example, benzaldehyde plus acetic anhydrous in presence of CH3COO negative Na positive at 450 Kelvin temperature gives cinnamic acid. Only aromatic aldehyde are used in Perkins reaction because they do not contain alpha hydrogen. Aldehydes containing alpha hydrogen undergo more rapid self-condensation in the presence of bases. Mechanism. In the presence of base, the acid anhydride loses a hydrogen ion from alpha carbon to form a carbonium, which add to the carbonyl group of aldehyde. The resulting ion, after protonation, forms an aldol-like product. This product undergo dehydration in the presence of acid anhydride to form a mixed anhydride, which get hydrolyzed to an alpha beta unsaturated acid. The complete mechanism is shown below by considering the reaction between benzaldehyde and acetic anhydride in the presence of sodium acetate. 12th is quinoine-Agel reaction. This reaction closely related to aldol condensation. It involves the condensation between an aldehyde or ketone and a compound having an active methyl group such as malanoic acid, malonic ester, and acetoacetic ester in the presence of a base which is usually an amine such as pyridine or piperidine. In general, the reaction may be represented as aldehyde or ketone plus active methylene compound gives C double bond C XY plus H2O. For example, malanoic acid plus formaldehyde in presence of pyridine gives CH3C double bond C having C2COOH molecules. The condensation product formed above can be decarboxylated to generate an alpha-beta unsaturated acid. Mechanism: the base remove say proton from the active methylene compound to form a resonance stabilized carbonium. This attacked the carbonyl carbon and the ions formed undergo protonation followed by dehydration. The mechanism can be depicted by considering the reaction between aldehyde and acetoacetic ester. 13. Manninic reaction. This is a reaction between an aldehyde, an amine, and a active methylene compound, which is usually an inelutionable ketone. The aldehyde usually taken is formaldehyde, and the amine commonly employed in dimethylenamine. The reaction can take place in neutral, acidic, or alkyne medium, and the product formed is popularly known as mixin base. For example, acetophenone inosable ketone gives mixin base. Mechanism: to start with formaldehyde reaction with amines to form a iminium salt. The iminium ions get attacked by the inert ions of the active methylene compound to form the final product. Manninic reaction can proceed through different mechanisms depending on the reactant and conditions employed. The above mechanism is for base catalyst reaction. 14th, the Wittig reaction. This is the reaction between aldehyde and ketones and a type of compound known as phosphorus yields to form substituent alkenes. Uh, the phosphor is generally used as aldehydes, triphenyl phosphorins, C6H5 thrice P double bond C R dash, where R and R dash may be equivalent to hydrogen or alkyl or aryl groups. The overall reaction may be represented as aldehyde or ketones plus any leading substituent alkenes and triphenyl phosphine oxide. It is clear that the reaction resulting in the replacement of carbonyl oxygen double bond O by the group double CR dash are themselves obtained by the action of base on suitable alkyl triphenyl phosphinium aldehyde prepared from alkyl halide or triphenyl phosphine. The base removed as proton from the alpha carbon atom of alkyl group of phosphine salt are generated to yield as shown below. The base generally employed in the above process is methyl sulfonyl carbanion, generated by the reaction between sodium hydride and the dimethyl sulfoxide or some organolithium compounds such as N-butyl lithium or phenyl lithium. The solvent commonly used as dimethyl formaldehyde DMF and tetrahydrofuran THF. For example, triphenyl phosphine plus methyl iodide give methyl triphenyl phosphinium iodide. Further gives, in presence of THF, gives methylene triphenyl phosphorin plus C6H6 plus Li. The yield obtained as shown above are not isolated but are directly made to react with the aldehyde or ketone in the solution form. Mechanism: the phosphorus aldehydes are resonance hybrid of the following contributing structures. Due to the negative charge on carbon, the yield exhibits carbonium character and initiate the nucleophilic attack on carbonyl carbon. The resulting addition product known as betaine undergo elimination of triphenyl phosphine oxide to yield the alkene directly or by a cyclic intermediate as shown below. The carbonyl compound as well as the yield used in the Wittig reaction may carry suitable substituent and therefore the reaction can be used for preparing wide variety of compounds containing C double bond C in desired position. In case of formation of alkenes, which can shown geometrical isomerism, example CH3, CH2, CH3 double bond CH3, the reaction gives a mixture of both isomeric in which trans isomer predominates. Halogenation of inosoluble aldehyde and ketone not included in syllabus. In the presence of suitable acid or base, the alpha hydrogens on aldehyde and ketone which contain alpha hydrogens can be easily hydrogenated at these hydrogens to form alpha haloaldehyde or ketones. Aldehyde or ketones give alpha haloaldehyde or alpha haloketones. It may be pointed out that the aldehyde and ketone having alpha hydrogen undergo tautomerism to form enols and are therefore called enantiable aldehyde and ketone. The halogenation reaction of such aldehyde and ketone proceed by different mechanisms depending upon whether the reaction is carried out in the presence of an acid or a base is discussed below. 15th base bromated halogenation in the presence of suitable base such as OH negative ion and CH3COO negative ion, one of more alpha hydrogens of carbonyl compounds get replaced by corresponding number of halogen atom. For example, acetone gives alpha bromoacetone. Mechanism. Bromination of acetone in presence of base was one of the earliest halogenation reaction of ketone to be studied in details. The rate of this reaction was found to be independent of concentration of Br2 while it was observed to be directly proportional to the concentration of the ketone and the base AB. This was attributed to the formation of carbonium intermediate as the rate determining step followed by a rapid bromination process as depicted below. In support to the above mechanism, it has been shown that under similar conditions of ketones undergo chlorination and iodination at exact the same rate as it undergoes bromination. This is in keeping with formation of the common intermediate in the rate determining step of all these processes. The above mechanism was further supported on the basis of stereochemical and isotopic studies of halogenation reaction. Since the base is actually consumed during the halogenation reaction, the reaction is often referred to the base-induced incidence or base-promoted reaction than merely base catalyzed. Since the base is actually halogenation of unsymmetrical ketones, in the base included halogenation of unsymmetrical ketones. Halogenation of unsymmetrical ketones. In the base introduce halogenation of unsymmetrical ketones of the type RCH2COCH3. Halogenation occurs at methyl rather than methylene group. This is because the electron releasing inductive effect of R group serves to decrease the acidity of the hydrogens attached to the methylene group, while the hydrogen attached to the methylene group are not affected. This leads to the professional formation of carbonium, which is more stable than second one. Furthermore, the base induced halogenation of monohalogenated ketones occurs preferentially at carbon atom already halogenated, provides that it still carry a hydrogen atom. For example, the electron withdrawing halogen atom carried by the halogen substituted carbon atom makes the hydrogen still attached to this carbon more strongly acidic and therefore more readily abstracted by the base. Moreover, it also helps to stabilize the carbonium ion third with comparison of to fourth. The professionally formation of CH3C double bond O CHBr naturally leads to the formation of the product as shown above. Acid 16 Acid catalyzed hydrogenation. The hydrogenation of carbonyl compound is also catalyzed by acid. For example, mechanism like the halogenation reaction in the presence of a base rate of acid catalyzed halogenation is also independent of the concentration of halogen but depends upon the concentration of the ketone and the acid, say Hz. Moreover, here too a given ketone undergo halogenation at the same rate irrespective of the nature of halogen employed, all other conditions being of course identical. Moreover, here too a given ketone undergo halogenation at the same rate irrespective of the nature of halogen employed, all other conditions being of course identical. In keeping with above observations, the mechanism of acid catalyzed halogenation involves the formation of an enol intermediate at the rate determining step 2 reaction. The enol found rapidly react further with the halogen as depicted below, considering the halogenation acetone. It may be noted that the acid merely serves as a catalyst and is not consumed during the reaction. Halogenation of unsymmetrical ketone. In the acid catalyst, halogenation of unsymmetrical ketones such as RCH2CO CH3 halogenation take place professionally to the methylene group. This is explained on the basis of the fact that enols is in which group is more highly substituted is more stable than therefore more readily formed. Now RCH2COCH3 can be formed following two enols: lesser substitution, lesser stability; greater substitution, greater stability. Eventually, the enol I, which ultimately leads to the halogenation of methylene carbon, is more stable than enol 1, which would result in halogenation as methylene carbon. Therefore, halogenation perfectly occur at methylene carbon. Reduction. Aldehyde and ketones can be readily reduced to form various products depending upon the nature of reducing agent employed as discussed below. 17. Reduction to alcohol. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols either by hydrogenation in the presence of catalytics such as nickel, palladium or platinum, or by reducing agent like lithium aluminium hydride and sodium boron hydride. The mechanism of the reaction has already been discussed in chapter 3. Mervyn Ponder of Berlin reduction. It is commonly used reaction for the reduction of ketones to secondary alcohols. The reaction is carried out by heating the carbonyl compound in isopropyl alcohol in the presence of aluminium isopropoxide, and the distillation of acetone can form the reaction mixture. The other functional group, if any, present in the carbonyl compound remain unaffected. Mechanism. The mechanism is of the reaction has already discussed in chapter 1. 18th. Reduction of methylene group. The carbonyl group in aldehyde and ketone can also be reduced by methylene group to form hydrocarbon. This is generally achieved by the following two methods. First is Clancy reduction. This involves the reaction of aldehyde or ketone with zinc amalgam and concentrated hydrochloric acid. For example, acetophenone give ethylene benzene in presence of ZnHg or HCl. This reaction works well for ketone but not for aldehydes. Mechanism. Several mechanisms have been proposed for this reaction. One of the proposed mechanisms is as follows. Wolff-Kishner reduction. In this method, aldehyde or ketone is heated with hydrogen or a strong base like potassium hydroxide or potassium tetrabutoxide. For example, cyclohexene gives cyclohexane. Cyclohexanone gives cyclohexane in presence of NH2KOH. Mechanism. The reaction is initiated by the formation of hydrazone of aldehyde or ketones which undergo subsequent changes as shown below. First, since Clancy reduction involves the use of concentrated HCl, it cannot be used for reduction of carbonyl compounds which may be also contain some other groups substitutably by the attack of acid. On the other hand, Wolff-Kishner reduction cannot be used for the compound which have may contain some alkyl sensitive groups as well. These reactions are particularly useful in the synthesis of alkyl benzene containing straight alkyl chain constituting a many carbon atom. For example, n hexylphenyl ketone in presence of ZnHg and HCl gives n-heptyl benzene. Third, reduction with Hi. Aldehyde and ketones can also be reduced to corresponding hydrocarbons by heating with Hi in the presence of red phosphorus reaction. For example, aldehyde or ketone plus 4 moles of I gives CH2O hydrocarbon plus H2O plus 2H2. 19. By molecular reduction. In the presence of magnesium usually employed in the form of an amalgam, aldehyde and ketone undergo bimolecular reduction to form symmetrical glycols, generally known as pinacols. The name of pinacols was initially employed from the glycol obtained from acetone, but it has come from to be used for all symmetrical glycols. Mechanism. Pinacol reduction involves the formation of a bond between two carbonyl compounds and proceeds through the following mechanism. Magnesium donates one electron each to two molecules of carbonyl compound to form an additive. This contains two unpaired electrons, one of each carbonyl carbon, which unites to form a carbonium-carbon bond to furnish the magnesium salt of pinacol. The salt is ultimately hydrolyzed to form pinacol. The mechanism is usually in the sense that it involves initial attack of oxygen rather than carbon. F20. Reductive amination. Many aldehyde and ketones changes into amines on treatment with hydrogen and ammonia or its derivative in the presence of catalysts such as nickel. The process is known as reductive amination and probably proceeds through the intermediate formation of amines. Aldehyde or ketones gives amines plus primary and further gives primary amine. This possibility of further reaction between aldehyde or ketone and the amine formed can be restricted by employing suitable proportion of the reactants. Oxidation. The behavior of aldehyde and ketone toward oxidation agents constitute the main difference in the chemical properties of these two classes of carbonyl compounds. Due to the free hydrogen atoms attached to the carbonyl carbon, the aldehyde are very readily oxidized, even by mild oxidizing agent, to form carboxylic acid having the same number of carbon atoms as the original aldehyde. Ketones, on the other hand, resist oxidation and get oxidized only by strong oxidizing agent. The oxidation reaction of aldehyde and ketone under different conditions are given below. 21st, oxidation of aldehydes. As stated above, aldehyde are readily oxidized by usually oxidizing agents such as KMnO4, K2Cr2O7, H2SO4 or C2H2CrO4 chromic acid, and dilute HNO3 to form corresponding acid. Example, CH3CHO gives CH3COOH. Mechanism of oxidation. Mechanism of aldehyde oxidation with different oxidizing agent are not well established. In the chromic acid oxidation of aldehyde, it is believed that aldehyde is first hydrated to a gem diol. The diol get oxidized by the formation of chromate ester as shown below. B. Reducing character. Since aldehyde are very easily oxidized even by mild oxidizing agent, they act as powerful reducing agent as illustrated by the following reaction. First, reduction of toluene reagent. Toluene reagent is an ammonical solution of silver nitrate which contains silver in the form of silver ammonia complex ion AgNH3 positive. On addition with aldehyde to the reagent, the aldehyde is oxidized to the carboxylate ion which is in ammonical solution formed the ammonium salt of the acid. The silver ammonium complex is reduced to metallic silver which get deposited at a silver mirror on the side of tube containing the solution. This reaction is therefore referred to a silver mirror test. Aldehyde plus toluene reagent give ammonium salt plus silver mirror. Second, reduction with failing solution and benzidite solution. Failing solution is obtained by mixing equivalent quantities of solution of copper sulfate and solution of sodium hydroxide or sodium potassium tetraacetate known as rosic salt. The resulting solution contains a copper tetraacetate complex which furnishes a small concentration of cupric ions. Benedict solution is comparable to Fleming solution and is obtained by mixing the copper sulfate of solution with a solution of sodium carbonate and sodium citrate. This is thus it contains a copper citrate complex which furnishes cupric ion. On reaction with aldehyde with Fehling or Benedict solution, the blue color of cupric ion is discharged and a red precipitate of cupric oxide is formed. The reaction may be depicted as aldehyde plus Fehling or Benedict solution gives sodium salt plus red PPT. The above reactions are not only gives ketones since they are easily oxidized and therefore do not act as reducing agent. Therefore, these are also used to detect the presence of aldehyde group and to form distinguished aldehyde or ketones. 22. Oxidation of ketones. It has already been stated that ketones are not easily oxidized. This is because oxidation of ketone invariably involves cleavages of carbon-carbon double bond. Therefore, it can be brought out only by strong oxidizing agents. The important oxidation reaction of ketone as follows. First, oxidation to carboxylic acid. Strong oxidation agents such as acidified potassium dichromate and concentrated nitric acid to yield a mixture of acid each containing lesser number of carbon atom than the original ketone. The reaction involves the attack only at the carbon atom adjacent to the carbonyl group. In case of asymmetrical ketone, the attack take place preferably at the adjacent carbon carrying lesser number of hydrogen atom. If both of the adjacent carbon have the same number of hydrogen atoms, carbonyl group remains linked preferably to the smaller alkyl group. Forbes rule, for example, CH3 CH2 CO CH3 2 CH2 CH3 gives CH3 CH2 C double bond OOH plus CH3 CH2 COOH. Second, haloform reaction. An important oxidation reaction of ketone is the haloform reaction of methyl ketones RCOCH3. It consists in reacting a methyl ketone with halogen in aqueous sodium hydroxide sodium hypoxyl solution. As a result, the ketone is oxidized to form the sodium salt of an acid containing one carbon atom less than ketone, and the same time haloform, chloroform, bromoform, iodoform is produced. The overall reaction can be represented as when a halogen is dissolved in aqueous solution, sodium hydroxide, the solution formed contains sodium hypoxyl as shown below. The reaction is also used for the test of methyl ketones when employed for the purpose of the hypothesis used of sodium hypodiide because the iodoform formed separate out as yellow PPT thus can be easily identified. The reaction is termed as iodoform reaction and may be depicted as follows. Mechanism: when methyl ketone is treated with halogen in aqueous sodium hydroxide, halogen take place at the carbon of methyl group, forming a trihaloketone. The carbonyl compound of this trihaloketone is then attached by hydroxide ion. As a result, cleavage of the carbon-carbon bond between carbonyl carbon and trimethyl attack group to take place. Carbon bond between carbonyl carbon and trihalomethyl group take place. This ultimately leads to the formation of a carboxylate ion and haloform is depicted ahead. Apart from methyl ketone, haloform reaction is also given by compound containing such groups that will form the methyl ketone structure under the condition of this reaction. Thus, secondary alcohols of the type also respond to the reaction since they are easily oxidized to methyl ketone structure. Acetaldehyde is the only aldehyde and ethyl alcohol is the only primary alcohol that also exhibit this type of reaction. Third, Beers-Willigers oxidation. The reaction involves the conversion of ketones into esters by reaction with pre-acids such as pre-benzoic acid, pre-acetic acid, or trifluoropreacetic acid. Formation of esters take place due to the introduction of an oxygen atom from the pre-acid bed between carboyl carbon and an alpha carbon. For example, RC double bond O R dash plus free benzoic acid give oxygen inserted here RC double bond O R dash plus C6H5C double bond OH. Cyclic ketones yield lactones in reaction. Mechanism: the reaction is catalyzed. The reaction is used by acid and involves the addition of pre-acid in the carbonyl carbon of ketone. The most important step in the reaction is the migration of R dash group to the carbon electron deficient oxygen as shown below. In case of unsymmetrical ketones, the tendency of a group to migrate called migratory aptitude to the electron deficient oxygen is in order: tertiary alkyl, secondary alkyl, primary alkyl, phenyl, primary alkyl, methyl. In case of substituted aryl group, the order is para-methoxyphenyl, para-toluene, phenyl, para-chlorophenyl. The migratory aptitude determines the final product formed in this reaction. This is an example of oxidation. For example, in the oxidation of acetophenone with prebenzoic acid, the final product is CH3COOC6H5 and not C6H5COOCH3. Because phenyl group have a greater tendency to migrate to electron deficient oxygen than a methyl group, it may be seen that the net result of Beers-Willigers oxidation is that one oxygen is inserted in between carbon of carboxyl group and resistant carbon of the group having greater migratory aptitude. 23. Cannizzaro reaction. This is a self-oxidation and reduction of deep or disproportionate reaction which is undergone by aldehyde having no alpha hydrogen. It consists in trait such as aldehyde with a concentrated aqueous or alcoholic solution or sodium or potassium hydroxide, while an alcohol and a salt of carboxylic acid are produced. For example, formaldehyde plus concentrated solution of NaOH gives methyl alcohol plus sodium formate. 2 moles of benzaldehyde plus concentrated solution of NaOH gives benzyl alcohol or plus sodium benzoate. Mechanism: the reaction involves the addition of a hydroxide ion to a aldehyde molecule to form an anion. The anion transferred as hydride ion to a second aldehyde molecule is shown below. Cross-Cannizzaro reaction. Cannizzaro reaction can also take place between two different aldehydes having alpha hydrogen. It is also known as cross-Cannizzaro reaction. It can lead to the formation of 4 different products. However, if one of the aldehyde is formaldehyde, the product consists of the most exactly sodium formate and the alcohol derived from the other aldehyde. Test for aldehyde and ketone and distinguish between them. First, test for aldehyde and ketone. Aldehyde and ketone can be detected by the following test. First, they form crystalline addition product with sodium bisulfate solution. They form yellow or orange color derivative with 2,4-dinitrophenylhydrazine. Second, distinguish between aldehyde and ketones. Aldehyde can be distinguished by ketone for following test. First, aldehyde form a silver Miller on warming with Toluene's reagent, but ketones do not. Second, aldehyde give red precipitate on warming with Fehling solution or Benedict solution, but ketones do not. Aldehyde give a pink color with Schiff reagent, but ketones do not. Schiff reagent is the solution of para-rosiniline hydrochloric chloride decolorized by passing SO2 into it. Third, distinguish between methyl ketone and other ketones. Distinguish between 2-pentanone and 3-pentanone. When a methyl ketone is treated with sodium hypodite iodine in the presence of sodium hydroxide, a yellow PPT of iodoform is produced. Other ketones do not give the test and thus known as iodoc test. This is used for distinguish between methyl ketone and other ketones. For example, 2-pentanone can be distinguished from 3-pentanone by the test as follows. Treatment with each of the produce form a drop of sodium hydroxide. 2-pentanone produce a yellow PPT of iodine while there is no reaction in the case of 3-pentanone. Treat each compound with a little iodide and a few drops of sodium hydroxide. 2-pentane produce a yellow PPT of iodoform while there is no reaction in case of 3-pentanone. for distinguish between acetaldehyde and benzaldehyde of formaldehyde. When treated with a little iodine and a few drops of sodium hydroxide, acetaldehyde gives yellow PPT of iodoform, but there is no reason in case of benzaldehyde or formaldehyde. It may be recalled that iodide is given those compounds which contain this group. In general, aliphatic aldehyde can also distinguish from aromatic aldehyde by Fleming solution. The former reduce Fleming solution while